Hello everybody and welcome to my video tutorials on Introduction to Computer Programming using Python Part 1. This is class 3 of the series, Analysis of Basic Problem Solving Methods. My name is Innocent Okoluku. The objectives of the class today is to discuss the idea of computer as a universal problem solving machine, to discuss the expression of real-life problems as mathematical or numerical problems, to discuss some problem-solving methods using real-life problems, to discuss how computers implement the solutions derived from the problem-solving methods examined. Now, before I talk about the motivation, we have not gone into Python programming yet. However, like I told you earlier on, computer programming originated from the backgrounds of electrical engineering and mathematics. So, at the low level, it is good for the aspiring programmer to understand the details of what really go on at the lower level, how the computer represents information, how information is processed. For you to be a good programmer, you really don't need to understand it to this level of detail that we want to examine in this part. There is a whole lot of app that you can design and make good wealth out of it without understanding the deeper details of how computers represent information that we want to study here. However, the reason why we are studying this here is because the knowledge is good for the aspiring computer programmer. You don't have to understand this detail very well before you can be a good programmer. So, don't let this class discourage you at all. You may find the content interesting, okay. If you don't find the content interesting, okay. From the next class, it will just be Python programming stuff and then we can enjoy the fun together. So, the motivation for this class is understanding problem-solving methods can enhance the inventive capacity of the aspiring software engineer / programmer. So, at the end of the class, participants should be able to explain how the computer is able to solve numerous real-life problems, analyze some real-life problems mathematically and develop solutions, express the solution of the analysis in terms of flowcharts, pseudocodes, algorithms, and Python code. Content. What is a computer? Problem solving using computers. Real-life problems as mathematical or numerical problems. How to solve it? We will be using the idea of G. Polyer. Steps to problem solving according to G. Polyer. Step 1. Understanding the problem. Step 2. Devising a plan. Step 3. Carrying out the plan. Step 4. Looking back. We will see an example in which we actually practice this thing. We do this thing practically using a very elementary example of robot soccer. And you will have your second homework or laboratory in this class. Because of the experience I've had teaching this course before, this same topic before, we are going to see a tutorial on how to do some calculations that will be required for you to do the homework / laboratory. What is a computer? Of course, we have been looking at computers from the very first class. We saw different forms in which a computer can appear, or various machines for which we can write software. However, we have not actually looked at the computer from the hardware perspective. From the hardware perspective, a computer is a processor connected to peripherals. So I have a very simplified diagram. So what we are seeing there is an example of a processor. For example, the Intel Core i7 or AMD Ryzen or whatever processor. So it's not just the processor, Actually, it is the processor that is the computer, but for it to function, it has to be connected to what we call peripherals. Peripherals are things like your display, that is your screen, your monitor, the kind of screen you have on your laptop or on your mobile phone or a computer LCD monitor, Bluetooth, sound, that's a speaker or and microphone, Wi-Fi, printer, etc. Whatever pieces of hardware that you connect to a computer to do something are all called peripherals. And one of the most important peripherals is a keyboard or a keypad or a touch screen that has a software keypad inside it. So, information flows between the processor and the peripherals, all of the peripherals. It's just that the keyboard is too big, that's why we just brought it out and separated it. It is also part of the peripherals. If you are going to take a course in computer science, a degree in computer science or related discipline, software engineering, computer engineering, you are likely going to take a course, several courses, really not one, in logic design and computer architecture, so on and so forth, where you actually design how to build a computer from scratch. And then you will learn that the computer processor itself is basically a very simple machine. Well, simple in the sense that it may contain millions of processors, but at the core of it is just an adder connected to some registers. An adder, something that can add two numbers. That's what a processor is. Basically, a computer is just an adding stroke arithmetic machine. You will learn about this in digital design, whatever name they call the course, computer architecture, logic design, so on and so forth. However, it can also store data using bits. A bit means binary digits which are stored as electrical switch states. You will also learn about this when you take a course in digital design. So the data storage of a computer is just like you have an array of switches, electrical switches on a wall. You turn some of them off, you turn some of them on. That is how the computer stores data. So you may have heard of 64-bit processor, or you have a 64-bit operating system on your machine. Let's simplify it. In those days there used to be 8-bit machines. In fact, even today there are 8-bit processors. 1, 2, 3, 4, 5, 6, 7, 8. So if we turn off this first switch, turn on the second one, turn on the third one, 0, that's off, on, off. So the computer actually has millions of these switches that can be turned on and off. What you have here, if you write it in binary arithmetic or as binary numbers, is already binary numbers. It is 0, 1, 1, 0, 1, 1, 1, 0. From elementary knowledge of mathematics, you know what it means in decimal number. And it also means something in the computer, as we will see later. So that is the basic operation of a computer. Another thing is, these switches are connected to each other. A block of switches make a specific component, probably a combinational logic component or a sequential logic component. Forget about the terminologies for now. Now these components are connected to each other using tiny copper wires, printed copper wires. That's why when you open any broken down electronic device or you open a computer up, you see very tiny lines of copper wire crisscrossing each other. That is to enable different parts of the processor move data from one part to another. You will also learn about this in digital design. So if a computer is a simple adding machine, something that can just add two things together, how come it is able to perform so many operations? It's able to do so many things. It can display computer graphics such as a web page, very colorful web page. It can display an image, can display an app window. You can use it to search for information very fast. You type something in Google and in less than a second you receive a lot of response. Computers are used to predict the weather. Computers can process videos, images, recognize something in them and make decisions. Computers can control a machine, control an aircraft, a robot, a CNC machine, that is computer numerical control machine. Those kind of machines, you put a piece of metal inside them and it just carves out a shape for you. Computers control a printer, control your car, so many areas where you can use computers in control. You use computers to play games. The applications of computers are very numerous and possibly cannot be exhausted. So, how is it that a computer is able to do so many things if it is just a simple adding machine? Here we have a colorful web page, as you can see here. This is a trading website similar to Amazon and the others. You can see how colorful the page is. Every area of the screen that has a color shade, a different color, the computer has a representation for that color. And that representation of the color there is represented by numbers, numeric numbers. So the reason why this pink is lighter than this pink is because the binary digits representing this pink is different from this, is different from the one representing the black, the ash, the blue, so on and so forth. Computers can process pictures. You can write programs in Python that can use a camera to look at the street and tell you there is a person on that street, there is a truck on that street, there is a car on that street, there is a bus on that street. So, the reason why the computer can be able to do all this processing is because the processes are all represented by using numerical representation or mathematical representation within the computer. Everything the computer is doing is just addition, subtraction, which is actually done by addition, multiplication, division, all of which are done by addition. So, to understand better what is happening, we are going to take a simple example. We have a window. Many of us who have been going to websites, many times we have to click OK after doing something. And the computer pops, or the website or the web page or the software pops an OK on the screen, which you can read. It's actually different. It looks like a button. You click on it and something happens. If we take such a simple example, how was the computer able to represent this kind of information on the screen? Such that the button for OK was distinguishable from the rest of the screen. So, we bring the picture down and what do? We divide the screen into pixels, or we pixelate the screen. So what we just did was like take a ruler and draw some lines across to make it look like a checkerboard. So we have divided the screen into pixels. This is exactly what a computer does. So, in the computer memory that is being shown on your screen at the moment, where you see the OK, it is actually made up of registers that are like this, like matrices. You know, I drew a register for you in the first few pages where I wrote some zeros and ones. So it's like now we have a register on this side. Now if you count the registers, you can know how many bits are these registers. So we have one register and another one packed close to it and another one close to it. That's exactly how it happens in the computers. Okay, so how did the computer use this to be able to show us that there is an OK button somewhere that we have to click? The computer did that by assigning numerical values to the pixels. You may have heard of the word pixels before, so we are going to explain exactly what they mean more clearly here. Pixel means picture element. So we divided the image into a screen, and what the computer did was now in the register assign 0 to parts of the screen or part of the register, because whatever you see on the computer screen is actually a part of the computer memory that was taken and beamed to the screen. So the computer decides that, okay, the parts of this register that are bright, we will assign the value of 1, because it is only 1 and 0 are the values you can assign to registers. And then it decides that the parts of the screen that are dark, we will assign it 0. So this is a very simple example. Now look at what happens here. We've assigned zeros to every part that is dark, and we've assigned ones to every part that is bright. Now we are going to remove the zeros and ones, and we are going to take every block that has a 1 or a higher percentage of 1. We represent it by a bright color, that is, turn the switch to 1. Turn the switch to 1. Turn the switch to 1. Now any part that has a higher percentage of 0 on it, we will leave it at 0. Any part that has a higher percentage of 1, we turn it to white. Any part that has a higher percentage of 0, we turn it to black or dark. And what do we end up with? Something like this. So you see, we have used the numerical values of the registers to represent the OK. Now look at the OK we have here. Looks like it's broken. That brings us to the idea of pixels. Now you may have bought a phone, and then one of the features of the phone, they will say it has a 5 megapixel camera, 2 megapixel camera, 10 megapixel camera. 1 megapixel means 1 million pixels, meaning that the register of the camera, how many pixels can it be able to hold? You see, if we count how many pixels we have in a row, there are 26 registers, and each of the registers have 50 pixels. So how many pixels were here in the first place?
So we have 50 times 26 equal to 1300 pixels. If 1 megapixel is about 1 million pixels, then 1300 pixels is just about 1 kilopixel, which is very poor.
Where we have a poor quality OK here on the side. So suppose we packed more registers and we multiply everything by 2. So we have 52 on this side and 100 on this side. In that case, our OK button, the resolution would have been higher than it is now. So what do we learn from this? The higher the pixels you have, the higher the resolution of the image you get out of. So we have seen now that everything we see on the computer screen is represented by using numeric values in the register. So let's take another example. Suppose we have a picture or an image, and we want to use the computer to determine whether there is a line on the image. Maybe you have a camera that is looking for lines in an image for one reason or another. You see, this is very practical. It is something that is used for processes every day, but it is a simple problem that we can consider to make us have a deeper understanding of how a computer actually uses mathematical and numerical operations to represent information and to perform operations. What do we do about this? Can you recall any ideas from coordinate geometry, those of you who love mathematics? So let's follow the same example we did before. The line is on a sequence of registers. Some parts of the registers must be 0, and other parts of the registers must be 1. We pixelate the image like we did before, turn it into a graph sheet, That is the way registers actually look like. So there are many ways we could have done this. We are trying to represent it using any mathematical formula that we know. There are many ways that could have been used to do this, but let's do it this way. So we say we will write a program that is going to be scanning through the register from beginning to the end and looking for a dark pixel. Scans from beginning to the end, and it's counting. The first time it scans from 1 to 50, it doesn't see any dark pixel. Then it comes to the second row, line number 2 or register number 2, and it scans from 1 to 50 again. It doesn't see any dark pixels. And then it comes to the third row and it starts counting again from 1, and then it gets to 25. It sees a dark pixel. So you say, I have seen a dark pixel, and that dark pixel is at 25 after counting 25. So it keeps counting again from here 26 down to 50. That's another 25. And then it comes to row 4 and keeps counting again until it sees another pixel. So it saw another pixel at x1 where it started from, then it counted 25 plus another 25 to x2 where it saw another dark pixel. So it will be 25 on this side plus 25 on this side. That is when it encountered another pixel. So it encountered the first pixel at 25. It encountered the second pixel at from 25 plus 50 more pixel counts. So it keeps counting. The next time it's going to encounter another dark pixel is going to be the previous pixel count plus 50. Consistently until it gets to the last pixel, where it doesn't encounter anyone after that. So we don't know how long the line is, but we can see from the sequence that the count follows an arithmetic pattern or an arithmetic progression. If you have done arithmetic and geometric progressions, which is under series and sequences in high school mathematics, you should be able to understand this. So we can use this general difference equation to actually capture the formula. So we say, given that the first item is 25, the mathematics textbooks will actually start at x0, but it doesn't matter. We are not learning mathematics here. We just want to know how computer represents information using mathematical stroke numerical ways to represent information and to perform operations. So we have an equation now that represents the line we have here. Now, if you look at the ideas of mathematics, there are other ways that you could have done this by using ideas from coordinate geometry. Already, this is a graph. This is the x-axis and this is the y-axis. And from the graph point of view, this should be 0. X is increasing, y is increasing. We could have taken ideas from coordinate geometry to determine whether a line is here or not, or anywhere else, or whether the line is slanted like this or like that. Okay, so if you recall any ideas of coordinate geometry, you can be able to do that and actually synthesize a formula which the computer can use to detect whether there is a line on the image. So you just write the program, take the image, divide it into pixels, make it a graph, and give the graph to the computer, and the computer can determine where the line is. So if you recall any ideas of coordinate geometry, you can be able to determine if a sequence of points make a line. The sequence of points must be collinear to make a line. You can do that. Recall the equation of a line, y equal to mx plus c, or the equation of a vertical line, x equal to k, so on and so forth. So Another area where computers are used is in weather prediction. This can be done from satellite, meteorological images. So what really happens in weather prediction? We may not need to know the details here, but we should learn how it relates to computers. So this is an example of a meteorological image that has been taken, and they want to use a computer to predict weather out of this. The same way we did it before. Divide the image into pixels because that is the way the register of a computer actually looks like. For the people in meteorology, each pixel at point I has an associated attribute, which is a combination of three numbers we call a tuple. So we say Pi, this big P, actually contains three parameters. If you want to represent a person, you can talk about his age, you can talk about his height, and you can talk about his gender. For weather, we use these three parameters to represent the particular pixel. So, the small pi there is pressure, T is the temperature, and H is the humidity. This data together with some formulas which they use in meteorology are used to actually predict the weather. So, as long as the images can be divided into pixels, it means that you can use computers to determine the prediction of the weather. Now, don't get confused with this. Like I told you before, our matrix representation is the easiest representation, where we represented one pixel with a 0 or a 1. So the curious students may want to ask, but you said one pixel can only be represented by a 0 or 1. Yes. So how come we have one pixel being represented by three items here? The fact is that registers can be grouped into blocks like that. So we have a sheet of registers in front and another sheet behind and another sheet behind. What you have in front here is the Pi, and the values of P, T, and I are inside other registers that are arranged behind it. So these three now form the value of the big Pi. That's what happened, in case you are curious. And you can learn more about this when you do logic design or computer architecture. So another thing that computer is commonly used for is searching for information, text processing, signal processing. How is the computer able to search for words like ransom, bomb, kill, etc. in random emails, chat messages, or telephone conversations? Text processing. What happens when you press a key on the keyboard or on the touch screen? So, when you press a key on the keyboard, you're actually pressing a switch. And the switch does not just generate a 0 or 1. Each key on the keypad or keyboard is coded. It is represented by something called an ASCII character, which has a decimal and binary equivalent. So I just put a simplified version of the ASCII character table. You can just go to the internet and type ASCII characters, and then you are going to see the full list, which is actually higher than this. ASCII means American Standard Code for Information Interchange. If you take a look at this part, you will see that almost everything on your keypad is represented. The space has a code, the decimal representation, and anything that has a decimal representation or whole number representation has a binary representation, which is 0 and 1s. So the space on your keypad, there is a dedicated code that has been assigned to it, such that the moment you press the key, the sequence of code is automatically generated for that particular key you pressed. This is the asterisk, this is for the inverted comma, so on and so forth. The codes for capital alphabets, capital letter alphabets, is different from those of small letter alphabets. So this is the way computers can understand each other when information is transmitted. So how does a computer represent the word bomb, for instance? Is it possible for us to write a program that just checks what somebody is typing in the computer, or just automatically reads an email message, a text message, and determine whether the word bomb is inside there? So from our ASCII table, the computer represented the word bomb by the sequence. First of all, B. If we come here and look for B, which is in small letter, we'll get 98. 98. O. 111. M. 109. And B, which ended it again, 98. So these decimal numbers in the computer are stored in a register, not as decimal numbers, but rather the binary equivalent of the register in the forms of 0 and 1s, which are just electrical signals. So we are still looking at text processing. The following transmitted conversation was intercepted by security computers which are constantly monitoring terrorist activities via remote sensing in a known region. This is a very practical scenario. Hide the bomb in town center by noon. Is it possible for us to detect this information automatically using the ASCII codes? Yes. First, represent the information in the ASCII code format using the ASCII table, and this is what we get. So can we write an algorithm to determine if bomb is in the conversation? Yes. All we just need to do is write the program so that it is checking for the ASCII equivalent of each of these letters in the conversation. So the first B, as we know from here, is 98. First thing we are looking for is we write a program that will be reading the message word by word until it finds the number 98. So read one word, compare it with the number 98. If you find the number 98, keep it somewhere, or raise a flag that says I have found the number 98. From the word bomb, after you find the number 98, the next number is supposed to be an O. So test whether the next number is an O. If the next number is not an O, then drop whatever you kept before. But if the next number is an O, then raise a second flag. You now have two flags. I have seen B, I've seen O. Check the third number then. Is it an M? 109? Yes. Then raise a third consecutive flag. I have seen M, and keep searching. If the next number is not a B, you are going to drop everything you've kept before and continue searching for B all over again. But this is B. You have at least been able to determine one word called bomb in the conversation. So what will happen in the class is students should just write their name and their surname or their full name, your name, middle name, surname, and try to represent it using the ASCII representation. So you have an idea how the computer actually represents your name whenever you want to log into Google or Yahoo or Facebook or whatever. That's the way the computer stores the information. So let's come to speech processing now. Whatever we have been learning in these few sections now is just to let us understand how the computer represents information, because it gives you a deeper insight as a programmer. The field of processing speech and text and image and video is a whole career on its own called signal processing. As a computer science student or a related discipline, electrical engineering, computer science, or similar discipline, you may likely take an undergraduate course in signal processing. 1 or 2 semester courses where you deal with all of this information we are trying to see. And then there you will find out that it is actually computers and processors that you use to process signals. So, whatever we are studying here, I don't expect that you have a deep understanding of it unless you take a course in signal processing. However, you should know how a computer can be used to represent information and process information. So we have a practical session now. You are going to use the audio recorder in your phone or your computer to record the words hide bomb. Speak it as loud as possible, but don't shout. Hide bomb. So there are many ways of recording sound on your phone or on your computer. I don't know which one is the best you would use, but you may install a software called Audacity on your computer for recording audio. I have found it very effective many times. Recording an audio should not be a big problem. Just go ahead, record an audio on your computer or on your phone and save the file as hidebomb.wav. So we are going to use it in a Python program and see whether Python can be able to read the file and actually plot the graph for us to tell us that it recognizes that this information has been stored somewhere on the computer. First of all, let me open Audacity. After you have opened Audacity, this is the record button. This is the stop button. So you click the record button and start recording. The moment you finish recording, click the stop button so you can come here and save. Hide bomb. We can now save the file. Export as .wav. That's the file that is easy for the Python library to understand at the moment. So I already had the file there before, but if you didn't have it before, just type the name here, whatever name you want to call it, click save. Okay, and it's going to show you this data that you really don't need to do now. We just need the file. Just click OK, and that will be all. You can now close Audacity and copy the file to the directory where you are going to keep your Python code, the same directory with the Python code. So I'll give you some time to do that. So how was the computer able to store the information? Is it possible for us to find the word bomb if we look at the stored information? Of course it is possible, as we are going to see. However, it is principles of signal processing that you use to determine that. We are not learning that in this course. We just want to have a general idea of what we can use computers and software to do. So in this code, we are going to use Python to plot the graph of what we recorded, the audio we recorded. Now, I am not expecting you to understand this code. It's just to show what you can do with Python. This is not a signal processing course, so you are not expected to understand this code at all, but just understand what you can do with Python in signal processing. So this Python code reads the file hidebomb.wav and then it plots the signal. The voice recording is hidebomb. So what it does is we are going to use some APIs, application programming interfaces, to load the file. You don't have to be familiar with this. So we imported NumPy, we imported Matplotlib, we imported SciPy, we imported IPython, and we imported NumPy. Don't worry about them. Just enjoy the fun we are going to have with this. So, in the next stage, we read the audio file. The file is actually hidebomb. Now, this code has been truncated to fit into this screen. You kept the file in a directory. you are supposed to list the full directory or use another built-in function to automatically detect where this file is. We will learn about that in future, not now. What is actually happening in this code is that a sound file, audio file, contains basically two parameters which you don't need to understand unless you are learning signal processing. One of them is called the sampling frequency and the other one is called the data. So we read the sampling frequency and the data from this file hide bump. So we take just a part of the data. Don't worry if you don't understand what is going on here. Later on when we learn about data types, list data types, you will understand what is going on here better. And then we print the sampling frequency. Then we play the audio. For one reason or another, my audio did not play back. I don't know why. But it's supposed to play audio here. But you don't have to worry about that. We are more interested in seeing the graph. Then we plot the wave of our recording. So PLT was imported from somewhere, and that is actually Matplotlib. This is the library or the API that you use in plotting graphs in Python, one of the APIs. So don't worry about whatever is happening here. We just say create the figure, plot the data, X label, write the X label, write the Y label, write the title of the graph, and show the graph. That's all. So now I am going to leave the presentation mode so I can copy the code to Python and run it so we can see the graph. Ensure that Visual Studio Code is open and you can create a new file and you are not in restricted mode. So as usual, we will just come here and copy the code and go to Visual Studio. So we say File, so we have copied the code back in PPT, and then we go to Visual Studio. We say File, New File, Python file, Ctrl V, we paste the file. Now we are going to save the file. This is the code file directory, took us directly here. So we can give it a name, representative name such as hidebump.py, hidebump.py. It has already selected Python for you here, so you can just click save. So our file didn't even have a comment name to show what it is doing, so we can just say hide. Even though it's not expressly required, it is a good programming practice to give it a descriptive name. Now you can either save first before you make corrections, or you can make correction directly. So we press the backspace to remove these red VT tags that are showing here. Ctrl S again, the file has been saved. Now what you see here is the point of the program that actually reads the wave file, but this should actually show the direction that the file was stored, but it's not showing it. I simply abbreviated it here for the purpose of making the code to fit into the PowerPoint slide. Now there is a way we can write the code to automatically detect which directory this file is at the moment. There is a built-in Python function that we can actually use to detect automatically which directory this file is, but we are not going to learn that now. We will do it in future. I want you to understand exactly how to get a file from a specific directory by using the absolute directory. If we run this program right now, we are going to have an error. It will tell us that it cannot find the file hide bump. In fact, experience is the best teacher. So let's try to run it and see what we have. Okay, So it says in line 12 there is file not found error, and that is in line 12. So what we are going to do is try to fix this. We will now go to the directory where the file was stored. It is better to keep the file that you want to read in the same directory as the Python program that is going to read the file. So we'll copy the absolute directory by pressing Ctrl C. This is the file here, and we'll come here and paste it. Now this directory is quite long. What we are going to do is use the / to replace the one we have here, all of it. So we've gotten everything we want here. We'll now copy it and paste to show the absolute directory to the file. Ctrl S. Now let's try to run this program again. Okay, so you can see that it loads the file and it looks exactly or similar to the way the wave was when we were doing the recording in Audacity. Well, if we go back to the PowerPoint slide, you will see some codes that I put here. This is not the first time I'm writing this program. That is why it ran without any error. But you who is running it for the first time, you will run into errors. In fact, if you are running it for the first time, you run into errors, because these libraries, these built-in application programming interfaces do not just stay in Python automatically when you install Visual Studio Code or when you install Python. You have to install them one by one from the Python repository. So if you got any error here, now I'm going to stop the program by clicking here in the terminal and pressing Ctrl C on the keyboard. So the program has stopped, and you see that the graph which was plotted has disappeared. We'll get back to it later. To clear the screen, press CLS, clear screen, and what you do is, if you run the program and you encountered errors, you will install NumPy to begin with. Just copy pipe install NumPy, place it here, press enter. It says requirement already satisfied. If you didn't have it before and you run the program is going to generate an error. It's going to tell you cannot find NumPy. So you have to install it like this. But you must have a good internet connectivity for you to be able to do these installations. After you have installed NumPy successfully and it is back to the command prompt, right click. So it says requirement is already satisfied. Again, because I installed it before. Paste. Requirement already satisfied. SciPy. Paste. Requirements already satisfied. So when you have successfully installed all of them, that is when you can now run the program, and then it plots the graph for you. Right. So if you are taking a course in signal processing in the future, you will understand what this is. The words that have been spoken are all here. You can pick each word from here. Even if several people are talking, you can be able to detect whatever the different people are speaking. But that is beyond the scope of what we are learning in this course. So that's what we can do with Python and computers. So you see the graph that was plotted is pretty different from this. They are not going to be exactly the same because your voice is different from my own. There may be some background noise when I was recording, or when you were recording, or someone else was talking, and so the graphs cannot be exactly the same. That doesn't mean the specific words like bump hide, which we want to get. That doesn't mean they cannot be extracted from the information. They can be done. So, if we agree that real-world problems can be expressed as mathematical or numerical problems, we may then adopt a mathematical or numerical approach to problem solving using computers. What we are trying to say here is the way computer represents information is actually numerical. So if you are going to go deeper into computer programming, have a deeper understanding of computers, you should learn to have an idea to express problems in numerical or mathematical situations. Like I said before, you don't require this to be a good or a successful programmer. Recall the programming process from the previous lecture. We define the problem, we plan the solution, we code the program, we test the program, and we document. Now, it is easy for you to plan the solution when you have an already designed analytical solution to the problem in the first place. We were trying to solve the problem for quadratic equation. It was easy for us to solve using our own design because somebody already produced the equation for quadratic equation. I also gave you a lab on the Heron's formula. Somebody already designed the Heron's formula. Suppose the problem you want to solve, there is no design. What do? Before you solve the problem, you have to design it yourself. You have to do all the design before you begin to talk about flowcharts, pseudocodes and algorithms, specifications and all that. So, how to solve it is more concerned with step 1 above, which is defining the problem. And we are going to follow the principles of G. Polya. You can just go to Amazon and Google G. Polya, how to solve it, and you will find the book I'm talking about. So we follow the principles aligned in that book. It is after we have followed those principles to derive a suitable formula, that is when we can progress to the stage of specifications, flowcharts, and algorithms. In fact, specifications can be actually a part of the solution provided by G. Polya. It can be intersecting. So, G. Polya outlined several steps to solving a problem. The first step is understanding the problem. The second is devising a plan. The third is carrying out a plan. And the fourth is looking back. First, understanding the problem. How do you understand the problem? According to G. Polya, you ask some questions and you make some deductions. First question is, what is the unknown? What do you not know? What are the data? What is the condition? Is it even possible to satisfy the condition? Is the condition sufficient to determine the unknown? Or is it insufficient? We could have just put these two in one line, but it is good to tackle them separately. Sufficient or insufficient? Or is the condition redundant? Is the condition contradictory? If possible, draw a figure. If possible, introduce a suitable notation, mathematical notation, just like the way we do in mathematics. Separate the various parts of the condition. Write them down. After that, we can now go to step 2. How do we devise a plan? Find the connection between the data and the unknown. Remember, data is something you have, something you see. But you are trying to use the data to get something that you don't know. Maybe build a model, build a formula. Find the connection between the data and the unknown. You may consider auxiliary problems if an immediate connection cannot be found. Is there a similar problem? Have you seen such a problem before? Or the same problem in a slightly different form? Do you know a related problem? Do you know a theorem that can be useful? Look at the unknown. Try to think of a familiar problem having the same or a similar unknown, or even the same data. We are still on devising a plan. If it is a problem related to one that you have solved before, can you use the previous solution? Can you use its result or its method? Should you introduce some auxiliary element in order to make its use possible? Can you augment it? Or can you just restate the problem all over again in a different way? Or you can go back to the definitions to review them if necessary. If you have done all these steps over and over, meticulously going through where you need to go through, you should eventually have obtained a plan of the solution. So, how do you carry out the plan? This is where we begin to follow the design aspect of the programming job. Use flowcharts, pseudocodes, algorithms where necessary, and write your program code. Check each step. Can you see clearly that the step is correct? Can you prove that it is correct, either by using data to prove it or by proving it theoretically? Examine the solution obtained. We are now in step 4, looking back at what we have done. Examine the solution obtained. Check the result. Check the argument. Can you derive the result differently? Can you see it at a glance? Can you use the result or the method for some other problem in future? When you have done this, you have developed a full working system. So, what we have been talking about is theoretical. We'll look at a practical example that will make us have a deeper understanding. Example: robot soccer. Robot soccer is a very interesting thing that has been happening around the world for some time now. If you just go to Google now, whenever you open a web browser and the fonts are very tiny, you cannot see what you want to see, just go and increase the size so that things can get bigger enough the way you want it. Say, let's say 150 is good enough. Now if you go to YouTube and you just Google robot soccer, you can see what's going on here. There is the RoboCup League that is currently been happening around the world now, and roboticists from across the world, from institutions around the world, come to play together, and they have a cup winner. It can be quite interesting. So this one you see here is a small size league. This was the 2019 Cup.
Now going for the long pass, back to Woenstroom. Beautiful tap here by Woenstroom. Goal, and the first goal scored by Team Water.
Alright, so a goal has been scored. So this is a small size league, and there is also the humanoid league, which is quite more advanced than the small size league. This is the humanoid league, RoboCup 2019, Sydney, Australia. Right, so I'll pause the video here so we can continue with our classes. We have an example of a robot soccer problem, an elementary problem. The question is, which side of a robot is the ball? There are two robots standing before a ball right there. For each of the robots, on which side is the ball? Is it to the left or to the right? So like I told you before, these robots are actually computers that have sensors and actuators connected to them. They have cameras up there in their eyes that they use to see the ball. They have actuators that they use to walk around, those limbs that they use to walk around. They have accelerometers that determine their speed. They have compasses that determine their orientation. They have gyroscopes that they use to balance. So many sensors and actuators. So for a simple problem like this, which is so easy for human beings to do, it's very simple for a human being to know whether the ball is in front of him or to the left of himself, as long as his eyes are not closed. But how does a computer represent such a problem? First of all, we follow the rule of G. Polyer. We want to understand the problem. What is the unknown? If the ball is on the left or on the right of a robot, that is the unknown. What are the data? The positions of the robot and the position of the ball, and the orientations of the robot, which directions the robot are facing. Just like for we human beings, if you ask me if the ball is in my front or my left or my right, it is going to depend on which direction I'm facing and the position that I am in. So what are the conditions? It depends on robot position and robot orientation. Other items may be considered. Now, if we look from the top on the field, suppose we have a camera that is directly looking from the top of the field, the way we look at a football field, what we have is going to look like, we have a robot in this position, we have another robot in this position, and both of them are looking at a ball. We have a ball in this position. So looks like this diagram, is it not? This is robot 1, this is robot 2, and this is the ball. To make things easier, we are going to rotate the figure on the right here, the drawing which I have here, to make things clearer for us. If we rotate it upside down, then we can define our parameters. Like before, what I told you before, we partition the view of the field and the position of the robots into a graph. Divide it into a graph sheet. Just like registers are. Okay? So let's see whether we can solve the problem. Robot 1 is in position X arrow 1, Y arrow 1. Robot 2 is in position X arrow 2, Y arrow 2. And the ball is in position XB, YB. You can see that our problem is now turning to an elementary trigonometry geometry problem. The next stage is devising the plan. Find the connection between the data and the unknown. So, what is our data? Our data are positions of each robot, orientation of each robot. The position is given to us by external sensors, maybe a camera that is looking at the robot, or something called robot odometry. You move the robot somewhere which is a starting point, and you tell the robot to move to a point, and the robot is using internal sensors to calculate its position, so it knows at this point it is here. Internal sensors with the assistance of external sensors. So this is data. This phi is also data because it is which direction the robot is facing, assumed to be 90 degree here. In reality it may not be 90 degree, but let's assume. Each robot has a compass that tells which direction it is facing now. That's the global sensor. The same thing for the second robot. Now, who determines where the ball is? An external camera that is looking at the feed from the top can determine where the ball is, or the robot has range sensors in combination with a camera that it uses to calculate the position the ball is, the distance the ball is relative to the position of the robot. So from its own position it can determine x, b, y, b. Now those are complicated stuff which we are not considering here. The only thing I want you to know is we know the x and y position of the robot, and we have also been given the orientation of the robot. Phi arrow 1 is the orientation or which direction robot 1 is facing. Phi arrow 2 is which direction robot 2 is facing. X, B, Y, B is position of the ball. Those are data that are given to the robot. Our problem now is to determine the angle of the ball relative to robot 1 and the angle of the ball relative to robot 2. So this is what we want to know. If we can know this, we can know whether the ball is to the left or to the right of robot 1. If we can know this, we can know whether the ball is to the left or to the right of robot 2. So that is our problem, for which we want to find a solution. Recall any formulas? If you look at this diagram we have here now, is a triangle. Can you recall any formulas that we can be able to use to solve this? Think of what you know from elementary mathematics. So, we want to carry out the plan now. Since we know x1 is the x position of robot 1, or x arrow 1, whichever, I abbreviated it as x1. x2 is the x position of robot 2, and x3 is the position of the ball. If we assume this, then using elementary trigonometry, we can be able to calculate theta arrow 1. The equation is theta arrow 1 is equal to the arctangent. Arctangent, that's this minus 1 means arctangent of YB minus y arrow 1, everything over xb minus x arrow 1. You will find the formulas in any O-level textbook. In the same way, theta arrow 2 is yb of the ball minus y arrow 2 xb minus x arrow 2. So if we successfully calculate this and this, and we know which orientation each of the robots is facing, those are all the data we need to know to determine whether the ball is to the left or to the right of a robot. So clearly, if you are facing this direction and this is the angle you have, and this angle is less than this angle, you know that the ball is to the right. But if this angle or this angle is bigger, greater than this angle, then you know the ball is to the left of the robot. If either of them, if this one is equal to this, it means that both of the angles are the same on a straight line. What does that mean? It means the ball is in front of the robot, any one of them. If both angles are equal, the ball is in the front of the robot. So you see that simple things that human beings and animals can do, in order for a robot or a computer to do it, we have to look for a mathematical equation to solve the problem. So how do we know if the ball is behind? How do we know if the ball is here, or here, or somewhere here? Simple ideas from coordinate geometry. You know every angle starts from here, from the right side, and then it goes counterclockwise to 180 degrees. So if this point is 0 degree, this is 180 degrees, the straight line, anything beyond 180 degrees is behind the robot. So what should be 180 degrees? If theta, either of the theta is above 180 degrees, then the ball is behind the robot. And this is one of the principles they use in those soccer robots to determine which position the ball actually is in relation to the robot. So we have found our solution. Looking back, examine the solution obtained, check the result, check the argument. We are now going to use real data to prove what we have just done now. Let x1 equal to 15,1. So this is the x position on the robot in the graph, robot 1, and this is the y position of robot 1 in the graph, and this is the x position of robot 2, this is the y position of robot 2 on the graph, and this is the position of the ball on the graph, xb, yb on the graph. We can just use the elementary formula which we used before. It's just theta arrow 1 is going to be arctangent. It's always y ball minus y1, y ball minus y1 over x ball minus x1, and that gives us arctangent of 19 over 5, which is, if you use your calculator, it is 75.26 degrees. You may get your answer in radians. We will see a tutorial to clarify this for us. In the same way, we calculate theta arrow 2. It is y bar minus y2, x bar minus x2. We take the arctangent, which gives us minus 37.23. Whenever you have a negative angle, you add 180 degrees to it, and that gives us 142.77 degrees. So if we assume phi 1, not theta, phi 1 equal to 90 degree, and phi 2 is the same as 90 degree, then we can conclude that the first one is less than 90 degree. Therefore, the ball is to the right of robot 1. While for the second one, the ball is to the left of robot 2. We are still looking back. Can you derive the results differently? Can you see it at a glance? Can you use the result or the method for some other problem? Okay. Now, I'm going to give you a homework based on this. Draw the flowchart for the ball position based on what we have done. Can you design the algorithm for the ball position problem? Can you write the Python program to implement the algorithm? You will submit the report to me on this email. For those students who are taking the course on campus, a due date for this lab report will be announced. This tutorial is necessary to help us do the lab stroke homework which I've just given. I haven't really taught you how to use Python to calculate angles, so it may be much more difficult if you don't have a background. However, the mathematical side we are looking at is purely elementary mathematics, ordinary level mathematics. Like I said before, you don't need to understand this class before you be a good and successful computer programmer. There's a lot of programming work that does not require this kind of mathematical stuff, okay? So, I just took the picture of the robot that we saw first, and then I turned it into the simple triangle problem that it actually is. So we have taken our problem, simple robotics problem, and turned it into the math representation. Let R1 be robot 1. This is now robot 1. Let R2 be robot 2. And let the ball be ball. In the diagram, R1 is at x1, y1. That is x equal to 4, y1 equal to 2. R2 is at position x2, y2. That is x equal to 40, and y equal to 4. Let the ball be at position x ball, y ball. That is x equal to 23 and y equal to 30. 23, 30. If we connect R1 to ball, we get the red triangle. This red triangle that goes all the way like this. And if we connect R2 to ball, we get the blue triangle. This blue triangle that goes all the way like this. From the red triangle, if we extract it, then we can calculate the tangent theta 1 by using what we know. Tan theta 1 equal to opposite. The line that is opposite to theta and the line that is adjacent to theta. So this line is now y ball. We are determining the length of the line. So tangent now becomes the difference between y ball and y1. So what we're actually doing here is, for tan theta 1, the opposite is this height. What is this height? It is 30 minus 2, which gives us 28. And also this length. What is this length? It is 23 minus 4, which gives us 19. So to get the theta, we now push the tangent to the other side and it becomes an arctangent. So we look for the arctangent of 28 over 19, and that is 0.9746 in radians. Your scientific calculator may likely give you in radians. Python will give you in radians. You have to convert it to degrees. So to convert it to degrees, you just multiply by 180 over pi, and that gives you 55.84 degrees. From the blue triangle, we calculate theta 2. We can actually calculate theta 2 directly by using the arctangent equation, which we have used before, but for simplicity, let us calculate the inner angle, because that will be easier for us to describe the tangent using opposite and adjacent. So we call it theta 2 asterisk. So in the same way, the tangent is opposite over adjacent. This is the opposite line over the adjacent line. So we're actually looking for this height is the opposite, and that will be 30 minus 4, which gives us the 26. The adjacent is this line below here. So we are looking for the length of the line, which is actually 40 minus 23. The adjacent is this line, the length of this line here, which is 40 minus 23, that is 17. That's where we got the 17 from. So we take the tangent, which gives us 0.992 in radians, convert it to degrees by multiplying it by 180 over pi. That gives us 56.2 degrees. So this angle is 56.2 degrees. But this is the actual angle we are looking for. So looking at the diagram, since we know that this is a straight line and the whole of the angle is equal to 180, we can subtract this from 180. We get that theta 2 is equal to 123.18 degrees. So this angle is greater than 90 degrees. However, we could have just used the arctangent formula to calculate theta 2 directly, just like the way we did theta 1. So all we just say is tan theta 2 is opposite over adjacent, y bar minus y2, x bar minus x2. So for y bar minus y2, we still get our 30 minus 4, which is 26. Then x bar minus x2 will be 23 minus 40, and that gives us minus 17. So when we calculate the tangent, we are going to get a negative value because of this minus that we have here. Convert it to degrees, we have minus 56.82. Whenever you have a negative number, you add 180 degrees, which gives us the same 123 degrees that we had when we calculated it by using this. So it's the same process. So we now know how to calculate the tangents by using the trigonometry and triangles. So the next thing we want to do is see a Python program that actually calculates the angles for us. We call this program CalcAtang. As you know already, this is just a comment. You can give it any name. We must import math. When you are doing mathematical operations in Python, you must import math. So if we take the theta 1 which we did earlier on, we just say theta 1 equal to math.atang 28 over 19. This theta 1 is going to be in radians. Convert it to degree by multiplying it by 180 over pi. So how do we call pi in Python? It is math.pi. So it is theta 1, which the one we got from here in radians, times 180 over pi. That gives us the value in degrees. The second one we are calculating theta 2 asterisk is math.atang 26 over 17. So the answer is in radians. We can convert that to degree, and this is what we've got here. So this was the last method we did, calculating theta 2 directly by using the negative which we got from the subtraction of opposite by adjacent. Convert what you got in radians to degrees here, you will have a negative value. So you can print everything out. Print theta 1 in radians, print theta 1 in degrees, print theta 2 asterisk in radians, print theta 2 asterisk in degrees, print theta 2 in radians, print theta 2 in degrees, and we are done. So I'm going to leave the presentation mode in PowerPoint so that we can copy the code and run it. Copy the code, go to Visual Studio Code. We still have our old program. You can either close this or just create a new file, paste it, save it, let's search for P. Python. Okay, I already got the file there before, so we'll replace it. Right, now let's clean up these errors from here. Control S. This kind of program that doesn't require you to enter an input before you get a result, you can actually see the answers using AREPL. So if I make a change to any one point here, you see what you have. We don't need to run it. Okay, theta 1 in radians is a very long number. Later you will learn how to truncate it. Theta 1 in radians is 0.97 approximately, in degrees is 55.8. Theta 2 in radians is 0.99 approximately, 56 in degrees. Theta 2 minus 0.991 in radians, in degrees is negative. So you could have just added it to 180 to get real angle in degrees. I'll leave you to do that. Sometimes you need to exercise your brain when doing programming. Alright, so if we had run the program, we would have had the same solution in the terminal. It doesn't make any difference at all. So we can now go back to the slide. So back in the slide, I think you have received all the background and all the tools you need to be able to solve the homework that I gave to you. So after you get all your angles in degrees, you now compare the angles you receive for each one of them, theta 1, theta 2. You compare them with phi 1 and phi 2. We are going to assume that phi 1 and phi 2, both of them are 90 degrees. And you can decide whether the ball is to the left of robot 1 or to the right of robot 1, or the ball is to the left of robot 2 or to the right of robot 2. So the bibliography, like I said before, if you go to Amazon and just type G-Polier how to solve it, you will see the book. Those of you who are interested in looking at this topic further, is up to you. But if you don't like this topic or you don't want to pursue it further, no problem at all. You really don't need this to be a good programmer. So you can follow the course from the next lecture to the end, where we'll be having fun doing real Python. The Python programs for signal processing, if you want to learn more about them, you can read this web page if you are interested. Our main textbook for the course still remains the book of Eric Mathis, Python Crash Course, a hands-on project-based introduction to programming. So, we have come to the end of the lecture today. Please like, share, and subscribe for more videos. Thank you, and see you in the next class.